Hello and welcome to the LPC3250 Overview Training module. In this module, we'll begin the presentation by introducing the LPC3000 family. Then, we will specifically look at the LPC3250. We will look at its memory and peripheral support, followed by a brief section on tools. LPC3000 family. The LPC3000 family is a family of microcontrollers based on the ARM926EJ-S core. Each family member consists of the following modules: CPU subsystem, multilayer AHP bus matrix, on-chip memory, external memory interfaces, system functions, communication peripherals, and a variety of other peripherals. NXP has a worldwide support channel and a network of third-party tool vendors that support this family in many ways. LPC32x0 series. The LPC32x0 series comes in 4 flavors: LPC3250, LPC3240, LPC3230, and LPC3220. The LPC3250 is the most featured device in this family, which includes the LCD and Ethernet controllers. The LPC3220 is basically the LPC3250 minus the 2 key peripherals. All devices in this series will have an operating speed of 266 MHz at 1.35 volts and 208 MHz at 1.2 volts. Now, we will specifically look at the LPC3250, starting with the block diagram. CPU subsystem. At the center, we have the ARM926EJ-S core integrated with 32 kilobytes of instruction and data cache. The CPU subsystem also comprises of the vector floating point coprocessor VFP9, which is critical for DSP-based applications. This core also supports embedded trace. Memory support. Except the LPC3220, all other devices in this series are provided with 256 kilobytes of on-chip SRAM. The external memory interface incorporates a NAND flash controller, SDRAM controller, together with an interface for SD card. Peripheral support. Let me highlight the key peripherals: Ethernet controller, USB block, which can be configured as a full-speed device, host or OTG, and the LCD controller. Connecting all the modules together is the multi-layer AHP bus matrix. Let's look at the multi-layer AHP bus matrix. The LPC3250 has a multi-layer AHP matrix for inter-block communication. AHB is an ARM-defined high-speed bus, which is part of the ARM bus architecture. For systems that have only one CPU, or two, for instance CPU and DMA, a simple AHB works well. However, if a system requires multiple bus masters and the CPU needs access to external memory, a single AHB bus can cause a bottleneck. There are 7 masters in this device, each with a dedicated bus: CPU instruction bus, CPU data bus, 2 DMA bus masters each with 8 channels, Ethernet controller, USB controller, and LCD controller. They interconnect with the various slaves over the AHP bus matrix. There will not be any arbitration delays unless 2 masters attempt to access the same slave at the same time. Let's look at the 7 masters in a little more detail. The data bus connects to external memory controller, the on-chip memories, and the slaves. The instruction bus connects to the memories. One of the DMA masters connects to all the modules, whereas the second DMA master connects to the memories and some of the AHP slaves. Also keep in mind, not all the peripherals may support DMA transfers. In a later section, we will cover the peripherals that support DMA transfers. The Ethernet controller, USB controller, and the LCD controller can transfer data to the on-chip SRAM and to external memory. Also note that even though there are 3 AHB slave ports connected to the EMC controller, they converge to a single external memory device, which limits access to one data transfer at a time. Let's review the key points of the multi-layer AHB bus matrix. The AHB bus matrix is a 7-layer, 32-bit, 133 MHz matrix that provides a separate bus for each of the 7 AHB bus masters. AHB matrix eliminates all arbitration delays as long as two masters are not attempting to access the same slave at the same time. Clocking structure. The clock structure is one of the most critical blocks of this device, so we will spend some time understanding this block. The diagram shown is a direct snapshot of the user manual. A simpler version of this diagram is provided in the next few slides. There are two main clock sources, main oscillator and the RTC oscillator. The main oscillator can take an input frequency from 1 to 20 MHz, typically 13 MHz, and the real-time clock oscillator can take an input frequency of 32.768 kHz. The RTC clock can also be chosen as a clock source for some of the low-speed peripherals like the RTC, PWM, ADC, key scan, and millisecond timer. There are 3 PLLs in this system: USB PLL, 39X PLL, and the H clock PLL. The USB PLL generates the 48 MHz clock that is needed by the USB interface. The 397X PLL multiplies the 32.768 kHz RTC clock to up to a 13 MHz clock, which can be chosen as sys clock or the input to H clock PLL. The H clock PLL can boost the frequency of its input to all the way up to 266 MHz. In the next slide, we will discuss the different clocks that can be derived from sys clock and H clock PLL output. Let's first derive the peripheral clock. The peripheral clock can be derived from either sys clock or the H clock PLL output. The H clock PLL output can be optionally divided by a number between 1 and 32. The green box indicates a mux. ARM clock. ARM clock is used by the ARM9 CPU. The SD card clock is derived from the ARM clock or an optional divided version of the ARM clock. AHB clock. The AHB clock follows a similar derivation as the ARM clock. The H clock PLL output can be divided by 2 or 4 before applying to the mux. DRAM clock. DRAM clock can either be sys clock or the H clock PLL output, and it has an optional divider of 2. So far we have looked at the various derivations, and now we have to focus on one key dependency. The top 3 muxes are controlled together. That means at any point in time you can either have sys clock or the H clock PLL output has an option for the next stage. The user manual of this device has a section called Clock Usage in Peripheral Blocks that explains the distribution of the various clocks in the system. Please review this section to understand which peripherals use which clocks. At reset, what are the clock settings? This slide shows the clock settings on reset. As you can see, the H clock PLL is disabled and the sys clock is used to source the peripheral ARM and AHB clocks. This mode of operation is called direct run mode. Operational modes. The LPC3250 can operate in three modes. Run mode. If the device is in run mode, it indicates that the application needs the CPU, AHB bus, or one of its peripherals to run faster than sysclock. In this mode, the CPU will run typically at 266 MHz and the AHB bus will run at 133 MHz. Direct run mode. If the device is in direct run mode, it indicates that the application does not need the CPU, AHB bus, and the peripherals to run faster than sysclock. This is the default mode after chip reset. Stop mode. This is the power saving mode of the LPC3250. In this mode, all CPU and AHB operations will cease. Clocks are stopped to all peripherals except the USB block. High core pin. The high core pin output may be used to save additional power during stop mode or during low frequency operation like direct run mode. It can be used to signal the external circuitry to lower the core supply voltage to 0.9 volts. This pin can be configured in software. The USB block will not be affected by the mode changes since it uses its own PLL. Stop mode. The stop mode incorporates a start controller which keeps track of the start sources. The start sources have been divided between interrupts and pins. Interrupts from ADC, USB, millisecond timer, RTC, and key scan can wake the device from stop mode. Similarly, pins related to the shown peripherals can also wake the device from stop mode. Mode transitions. On reset, the device will come up in direct run mode. From here, the device can switch to either stop mode or run mode. Let's assume the device wants to switch to run mode. This can be achieved in software by writing 1 to bit 2 of the power control register. By resetting this bit, the device will re-enter direct run mode. The device enters stop mode by setting bit 0 of the same register. Wake up from stop mode is configured in the start controller. It is not possible to switch directly from stop to run mode and vice versa. Let's look at the on-chip memories and the external memory interfaces that the device offers. On-chip memory. All devices except LPC3220 are equipped with 256 kilobytes of on-chip SRAM. The LPC3220 has 128 kilobytes of on-chip SRAM. The bootloader resides in a ROM, and the chip can boot from various sources including NAND flash, UART, SPI memory, or static memory. There are three interfaces for external memory. One external memory controller to interface to static and dynamic memories. Two NAND flash controllers, and one SD card interface. Some key points relating to external memory interfaces. The external memory interface supports 2 chip selects for dynamic memory and 4 chip selects for static memories. Both the NAND flash controllers share the same pins. Hence, only one controller can be used at any time. The multi-level NAND flash controller has a 528-byte buffer to avoid CPU intervention while loading. NAND checksum is also performed in hardware. The SD card controller is a standard interface and supports the SD card memory specification 1.01. Let's move on to the peripheral section. In this section, we will cover the interrupt controller, communication peripherals, timers, other peripherals, DMA controllers, and power management. Interrupt controller. The interrupt controller is made up of 3 blocks: main interrupt controller, sub 1 interrupt controller, and sub 2 interrupt controller. The output of the interrupt controller drives IRQ and FIQ to the main CPU. Interrupt priority is fixed and is in direct correspondence to the way the peripherals are connected to the controller. As an example, the Ethernet interrupt is connected to the main interrupt controller, whereas the USB interrupts are connected to SIC1. When an interrupt occurs, the application has to visit the MIC, SIC1 and or SIC2 status registers and to search for the source of the interrupt. Also, as a note, the interrupt controller does not operate in stop mode. The start sources connected to the start controller will help the device to exit stop mode. Now, let's look at the peripherals that will be used for system communication. The USB block can be used either as a device, host, or in an OTG configuration. It supports all 4 transfer types and does not support high speed. It has its own dedicated DMA controller. There are 2 SPI and 2 SSP controllers. The SPI controller can only be used in master mode with bit rates up to 52 megabits per second. The SSP controller has 8 frame FIFOs for both TX and RX. Each frame can accommodate between 4 to 16 bits. Ethernet MAC is also supported and it interfaces to the external PHY using the MII or RMII protocol. Please be aware of this note while using the Ethernet interface. The MDC frequency should not be typically more than 2.5 MHz. In the LPC3250 implementation, the minimum attainable MDC frequency will be 3.714 MHz. To avoid this issue, either limit the H clock to 52 MHz or select an Ethernet PHY that supports MDC frequencies above 3.714. This behavior will most probably not be noticed because most external PHYs support higher frequencies. Chugging along with communication peripherals, this device supports 7 UARTs, out of which 4 are standard UARTs and 3 are high-speed UARTs. The 4 standard UARTs support fractional baud rate generation, and UART 6 has support for infrared communication. 2 I2S interfaces are provided to aid in audio communication. 2 I2C interfaces are provided which can be operated as master, slave, or in a multi-master environment. Timers. This slide is broken up into 2 blocks. The high-speed timer, millisecond timer, and the watchdog timer are inherent to the LPC3000 family. The 4 general-purpose timers are adopted from the LPC2000 family and explained in the next slide. Some key points from the first block. The high-speed timer is clocked by the peripheral clock. The millisecond timer is clocked by the 32 kHz RTC clock. The watchdog can be used as a standard timer if not used as a watchdog. General purpose timers. The 4 timers can be used as timers or counters. Each timer has 4 capture channels that allow the device to take a snapshot of the timer value on input signal transition. Each timer also has 4 match registers that can drive 4 external pins. Real-time clock. The real-time clock in the LPC3250 has an ultra-low power design and is ideal for battery-powered systems. It has a dedicated 32 kHz oscillator, 128 bytes of very low voltage static RAM, and interrupt mechanisms using match registers to come out of stop mode. Also, a point to note is that the RTC power domain is isolated from the rest of the chip. An output pin is also included to assist in waking up the chip when it has power removed from all functions except the RTC and battery RAM. PWMs. There are two 8-bit PWMs and two 32-bit PWMs in the LPC3250. The two 8-bit PWMs are clocked by the main peripheral clock or the 32 kHz RTC clock. The two 32-bit PWMs have 7 matched registers to allow up to 6 single-edge control or 3 double-edge control PWM outputs. Both the PWMs can be run synchronously. The PWMs can be used as standard timers if the PWM mode is not selected. LCD controller. The LCD controller provides all of the necessary control signals to interface directly to a variety of color and monochrome LCD panels. As we saw in the multi-layer bus matrix slide, this controller has an AHP bus master interface. The AHP master interface transfers display data from a selected slave to the LCD controller DMA FIFOs. It can also be configured to obtain data from Onchip SRAM, variety of off-chip static memories, or off-chip SDRAM. It has dual 16D programmable 64-bit white FIFOs for buffering incoming display data. It has hardware cursor support, which reduces software overhead associated with maintaining a cursor image in the LCD frame buffer. It has a 256 entry 16-bit palette RAM arranged as a 128 by 32-bit RAM. It supports Little and Big Endian and Windows CE data formats. LCD panel supported. This slide provides a general listing of TFT and STN panels that are supported by the LPC3250. Wrapping up with peripherals. The LPC3250 includes a touchscreen controller. The touchscreen controller can operate in two different modes, auto and manual. In auto mode, the touchscreen will automatically collect the X and Y coordinates of the pressed position. In manual mode, the controller can be sequenced entirely by software to collect the coordinates of the pressed position. The touchscreen interface pins have robust ESD protection. The controller also operates as a 3-channel ADC. When the TSC is configured as an ADC, it will be a 3-channel 10-bit successive approximation converter. The analog portion of the ADC has its own power supply to enhance the low noise characteristics of the converter. A total of 87 pins can potentially be used as general purpose outputs, general purpose outputs, and general purpose inputs. An automatic keyboard scanner function is also provided that supports 8x8 keys. Summarizing DMA controllers. The general purpose DMA controller has 8 channels. Peripherals that support DMA are the SD card, high-speed UARTs, I2S ports, and the SPI interfaces. As also mentioned earlier, dedicated DMA controllers are available for USB, Ethernet, and LCD controller. Now let's explore the power management options in the LPC3250. Low voltage operation. The LPC3250 can be operated as low as 0.9 volts. The on-chip PLLs cannot be used at this voltage, so the chip will be operating at a lower frequency. This is suitable for very low power standby modes where system operation is required but performance can be compromised. The high core pin can also be used as an indicator to switch to a low voltage. Stop mode. This is the operational mode of the LPC3250 where the multi-layer AHP bus matrix is disabled and the CPU clock is stopped as well. System operation on RTC clock. The RTC oscillator uses a 32 kHz crystal and runs at a much lower power than the main crystal oscillator. The RTC397X PLL multiplies the RTC clock to a frequency which can be further multiplied by the main PLL to generate the greater than 200 MHz CPU clock. Powering down SRAM. The Onchip SRAM is broken up into 4 blocks of 64 kilobytes, and they can be individually powered down to save power. Power domain switching. The RTC clock is on a separate power domain and also has 32 words of low power SRAM. To save the maximum amount of power, the microcontroller power can be turned off altogether while keeping the RTC alive with some critical system information that can be saved between power cycles. This also eliminates leakage current power consumption. Programmable clock enabling. Each peripheral and the AHP bus matrix has a selectable clock enable bit. Thus the application can control which combinations of peripherals to enable for a particular system design and also when to enable them. Further, several peripherals have local power savings such as sleep modes. AHP bus matrix clock control. The AHP clock can be divided to run at a lower frequency so that the entire matrix can run at a lower frequency. Power numbers. Presented on the slide are the power numbers for the 3 operational modes of the LPC3250: run mode, direct run mode, and stop mode. Also a point to note, in direct run and stop mode, the chip voltage can be lowered to 0.9 volts. Tools. In this section, we will cover ETM9 with ETB, we will cover the PHYTEC evaluation board, we will talk about platform operating systems WinCE and Linux, RTOS support, and the common driver library. ETM9 with ETB. The ETM9 provides real-time trace capability for deeply embedded processor cores. It outputs information about processor execution to the embedded trace buffer. The embedded trace buffer stores trace data produced by the ETM in a 2K SRAM that is used for instruction and data history storage. A software debugger that allows configuration of the ETM using the JTAG interface is then able to display the trace information that has been captured in a format that a user can easily understand. Tools like ARM RealView Eyes and the RealView Debugger will support this feature. PHYTEC Evaluation Board. NXP has partnered with PHYTEC to provide a low-cost evaluation board for the LPC3250. The basic kit is available for just $399. Has an add-on option. A Hitachi LCD with integrated touch is also available. The board will be accompanied by the PHYTEC Spectrum CD that will include complete electronic documentation, demo programs, and evaluation software development tools. OS support. LPC3250's ARM9E core with built-in MMU makes it possible to run platform operating systems like WinCE and Linux. With regards to WinCE, Arduino provides a comprehensive solution, and NXP also provides a free port. A Linux port is also coming up very soon from NXP. In addition to platform operating systems, real-time operating systems like Seger's Emboss and Micrium's MicroSEE OS2 are also supported on the LPC3250. NXP has partnered with Arduino, a gold partner with Microsoft Windows Embedded, to provide a comprehensive solution for WinCE. Arduino provides WinCE BSP for LPC3180, LPC3250, and the LH7A404. Here BSP means board support package. As the name suggests, BSP includes software drivers that support a specific evaluation board. In the case for LPC3250, this board support package is tailored for the PHYTEC evaluation board. The board support package will include support for most of the peripherals and interfaces that an application would need to get up and running on the FITech board in a matter of minutes. This package is available for evaluation in the form of a binary BSP. Under NDA, NXP customers can also get full access to the source code for 20 days. The complete product presentation can be found at the provided link. In order to provide more options to our customers, NXP also provides a free Win 6.0 BSP for the FITech evaluation board. For more information on this package, please visit the NXP website. Seger BSP. Seger provides a BSP for LPC3250 and provides various packages. EM-File is a file system supporting different memory interfaces. EM-Win is a graphic library package. EMB-OS is an RTOS, and EM-USB is a device stack supporting different USB classes. MicroSEE OS2. The MicroSEE OS2 RTOS is ported to the LPC3250 together with MicroSEE Probe. MicroSEE Probe is a universal tool enabling embedded developers to monitor embedded systems in a live environment. By eliminating the need to stop an application in order to get system feedback, MicroSEE Probe saves considerable development time by visually allowing users to see the internals of a running embedded application. The provided web link will provide details on MicroSEE OS2 and MicroSEE Probe. Common Driver Library CDL. The CDL encapsulates LPC3250 peripherals and its specific functions by providing an API interface. It provides support for Code Sorcery GCC, Kyle, and the IAR toolchains. This library will be covered in great detail in a separate video presentation. A complete tool and software solution. Several board support packages are provided for the low-cost FITech evaluation board that includes both platform-based and real-time operating systems. NXP also provides a common driver library that encapsulates the LPC3250 in many levels and includes support for several toolchains like GCC, Kyle, and IAR. The LPC3250 has great support from the embedded ecosystem and provides several options to the customer to choose from. This brings us to an end of the LPC3250 overview presentation. Please leave your feedback and any suggestions that you might have in the comment box. Your inputs will help us improve the training experience in the LPC zone. We are adding new training modules all the time at nxp.com/lpczone. So we encourage you to register and we will send you email updates when new videos get uploaded. Thanks for watching this video and we look forward to seeing you again.